Okay, well, today is the day before our first exam in this class, right? And you wanted us to talk about what's going to be on the exam. So let's do that, but let me finish off some material that was not necessary for you to do your homework, but nevertheless that is good to, we'll finish up a few things. Here, the topic is what is an expression tree and how does it work? And so we'll do that. That'll take maybe 15, 20 minutes, and then we'll spend the rest of the time talking about the exam. So the last thing that we want to take a look at is what is an expression tree. Now, do you remember how we defined a list? It's always recursive. And what's the base case? What is a list? The empty list is a list, and then a what? Non-empty list has how many parts? Two. And they are the what? The car and the cooter. So the car is the first element, and the cooter is the rest of the list. And then we said the definition of a tree is what? The empty tree is a tree, or a non-empty tree has how many parts? Three parts. The root, value, and the left child and the right child. Okay, well, what do you suppose an expression tree is going to be? It's going to be, again, it's going to be recursive, and there's going to be a base case and a recursive case. But look, you guys, in contrast to the other definitions, there is no such thing as an empty expression tree. Are you with me? Now, this is conceptually, mathematically, an important thing. Because what we're saying here is the base case is a number is an expression tree. So we never deal with empty expressions. Do you see what I mean? The empty expression is not the base case. Instead, a number is the base case. Are you with me? A number is the base case. And then a non-number tree has three parts. And what are these three parts? Oh, and by the way, what kind of notation does this look like? A left operand, an operator name, and a right operand. What does this look like? What sort of notation does this look like? Infix. This looks like infix notation, doesn't it? So, what is a non-number tree? A left operand, which is an expression tree, an operator name, and then a right operand, which is an expression tree. Is everybody with me on this? Okay, so let's go to our demo. And check this out. So here's our demo. So what did we say the base case of an expression tree is? A number. So how are we going to check for that? Well, fortunately, watch this. Number. And what do you think? Is that a number? No. No. And what do you think? Is that a number? No. And what do you think? Is that a number? Yes. Okay, does everybody see how number works, right? Okay, so now what we're going to do is we're going to take a look at an expression, and here we have defined my expression to be this expression. Now, does everybody see, so if I just type in my expression, because it was defined that way, that's what it is. Now, what does it look like my expression is? What kind of, what notation are we using here? Infix, but it's fully parenthesized. Okay, so it has to be parentheses. Are you with me? All right. So now, actually, Yeah, so that's my expression. Now, number is built in. Oh, you know what I should have done? On the slide, I should have had constant b instead of number because I think, so what do you suppose constant, quote, a is? False. But what is constant 7? That's true, okay? So what is, constant is the same thing as what? Number. So number is built in. Yeah, I guess on the slide I should have said a constant. Yeah, that was, I need to change the slides. So the slide should have said a constant is the base case. Are you with me? And then otherwise it's not, it's a non-constant. All right. So now check this out. What do we need to do in order to be able to, what do we have to have in order to be able to manipulate expressions? Well, how about this? Operator, my expression. What do you suppose the operator of my expression is at the top level? Plus. Are you with me? And what should the left operand of my expression be? One. And what should the right operand of my expression be?
2 times 3 minus 5.
Right, 2 times 3 minus 5. So does everybody see that this is very similar to a tree, right? So look, let's go to our, so look, so here is the definition of my expression, and it's 1 plus 2 times 3 minus 5, and it's in the same way that a tree has a non-empty tree has 3 things, a non-constant expression has 3 things. And they are and you can view it as in tree form like this. So does everybody see how that works? Mm-hmm. It's just like, only this time what's in the inside of an interior node? It's always a what? One of these inner nodes. You know, a non-leaf node. A non-leaf node is, they are the operators, then what's always on the leaves? Constants, yeah. Are you with me? And then you see, does everybody see how this works? Right? Okay, so what is this? Because it's fully parenthesized, there's no ambiguity as to what happens first. First you do the 3 minus 5, yeah? And then you multiply that times 2, and then you add 1 to that. Yeah? And so that's the picture of the tree. And so, now this is super easy, I think. Can you tell me then what is the definition of operator? What's the operator? The C, well, oh, it's not, well, we don't have root here. We just have, left operand and right operand and operator. So say it again, the car of the cooter. Now, is everybody clear are you clear on that? The car of the cooter, okay, so that's the CADR. And what about the left operand? Just the car, good, excellent, you guys are good. And what about the right operand? The cooter of the,
What's the cooter of the cooter?
the cooter of the cooter, how do you spell that? Is it CADDR or is it CDDR? I think the CADDR would be the car of the cooter of the cooter. Are you with me? Are you with me on that? So that, oh, but it is the car. Wait, is it the car of the cooter? Yes, it is the car of the cooter of the cooter.
Why would it be?
Oh, are we good? No, you hold on. Okay, okay. Here. Let's do my expression. Okay, as everybody agrees with this. Now, so what would just the CDDR of my expression be?
The cooter of the cooter.
That's the cooter of the cooter. But now, what's the cooter of the cooter? Yes, yes, it's going to be that. An extra, are you with me? Because it's a list. It's the list of the last thing in the list, but it's a list of that. Because the cooter is a list. So to extract just that, what do we need? We need the CADDR of my expression to get just that. Is everybody good? It's the car.
That's the car of the cooter of the cooter.
That's the car of the cooter of the cooter. There is a cooter, a CDDR, but that's not what we want to get the right operand. Okay, now check out this demo. Are you ready for this? What happens if I do plus and press return? Do you know this yet? Do we know this yet? Plus, what's that going to give us? A procedure, right? Okay, and so everybody agrees plus is a procedure. But what happens if I do quote plus?
Plus 5.
Yes. So now here's the point. What's the difference between plus and quote plus? Quote plus is the what of the procedure? It's the name. Are you with me? Plus is the procedure. Quote plus returns the name of the procedure. Is everybody with me on this? And similarly, what is asterisk? That's procedure. But then what is quote asterisk?
Asterisk.
That's the name of the procedure. Are you with me? Now watch this. In order to manipulate our expression tree, what we are going to have is a function called lookup value. Look up value. And if we say lookup value quote plus, now what are we giving it? Now tell me, what is the argument that we are giving lookup value? Are we giving it a procedure or are we giving it the name of a procedure? We're giving it the what? The name of the procedure. And what do you suppose this is going to return? We're giving it the name. What is it going to return? The procedure. Now, is everybody clear on what's happening here? And similarly, if we do look up value, and we can do this for multiply, and it's going to give us the multiply procedure, and we can do it for look up value. We can do it for, this is programmed to do all four. So if we give it the name, so this is a single quote hyphen, right? It's going to return the what? The minus procedure, and we can also do it for divides. Are you with me? And it's going to return the divides procedure. Now, check this out. Suppose we define, and this works in general. Suppose we define my symbol. Suppose we define my symbol to be this symbol, quote, the @ symbol. Are you with me? So that defined it. And if I just type my symbol, what happens? What comes out? Obviously. @ Yeah? All right. And now, check this out. We have equal, E-Q-U-A-L. So equal. And you know, remember we had the equal sign once before, but this is not the equal sign, this is the equal. And so how does equal work with this? If we say equal, and then we say my symbol, quote, at, then what will equal return? What will equal return? Oh, sorry, thanks. Ooh, that's nice for not. Symbol, quote. All right, so now what will this return? True. On the other hand, if we say equal, and we say my SYM, my symbol, and is that equal to the plus symbol, then the answer is obviously false. Are you with me? So here's my question. Write lookup value. Now, how many parameters does lookup value have? 1, yeah? It has 1. And we'll call it name. Now, what do you suppose we should use here? Condition. Yeah, cond. Okay, and what will we check? Equal if the first condition will be, the first test on our condition will be if the name equals what? Now, and what is this quote plus? That is the name of the function, right? What will we return? All right, you guys, what did you see what? Say it again?
Plus.
Yeah, we return the plus function. Now, does everybody see what we're doing here? The difference between the name of a function and the function. Are we good? This is a really good last example of the functional paradigm, because we're talking about functions here, returning functions, giving the name of a function and then returning the function itself. And then obviously, what's the rest of it? Equal name at star to return what? Star equal name hyphen, return the minus function, and equal name slash, return the divide function. Is everybody with me? Else error unrecognized name. Are we good? Okay. And now, you guys, the culmination of the functional paradigm. What do we want to be able to do to my expression? Now, what's the loop that governs this thing? What's the loop that governs this thing right here? The read eval print. So once we read it, what do we want to do with it? Evaluate. So check this out, you guys. Evaluate my expression. And what should come out? Do you remember what my expression was? Here, let's go up. There it is. What should come out? Well, what's 3 minus 5? Times 2 is negative 4 plus 1 is negative 3. So what should come out when we do evaluate my expression? Boom. All right. The last one, our last functional paradigm function. Aren't you sad to say goodbye? Define, evaluate. What does evaluate take? An expression, so one parameter. So lambda, expr for expression. And what's the base case? Constant. So if what? If it's a what? Constant, return what? Right. If constant expression, return the expression, which is just a constant. Yeah? Otherwise do what? Otherwise, what do we return? Otherwise, what do we return? The what? Well, what do we...
Operator of one thing. Of the expression.
We... say that again? You have to evaluate, well, what do you have to do? You have to evaluate the what? No, let's think about this. Let's think about it. Good, this is good.
Catter,
Okay.
CADDR,
No, we're not using catter. Let's use left operand. We don't need to do where you CADDR. Let's do left operand. What do we have to work with? Left operand, right operand, and what? Operator. Are you with me? So what is it?
Operator expression, left operand expression, right operand expression.
Well, it's parentheses, isn't it?
Yeah, it's double parentheses.
Well, is it double?
Yeah, I think so.
Oh, well, it's isn't it the,
left operand, and then evaluate.
right?
Right operand.
Yeah, evaluate the evaluation of the left operand and the evaluation of the right operand.
Yes.
But then what do we have to do with the evaluation of the left operator and the operand and the evaluation of the right operand? We have to operate on it.
Yeah.
So then, but now in scheme, the operator comes first, right? So what do we do? Okay, so are we good? So what's coming up next?
Operator.
It's the operator, but then, oh, well, haha. We have to look, but what we're given, I mean, what operator returns is the what of the operation. It's the name of the procedure. So what do we have to do? When yeah, so we look up the value of the operator of expression, and that returns the function, and that function is what goes right. That function is what goes. Oh shoot! Now I just spoiled it. Okay, so here, oh, darn it, did it again. Well, there it is. Well, you guys know what it is anyway. Are you with me? So you look up the valuation. You look up the value of the operator of the expression. That returns the function. So it's left parentheses that function, and then the evaluate of the left operand of the expression and the evaluate of the right operand of the expression. Okay. Well, anyway, are we good?
Yes.
I think that's good. All right. So that finishes the functional paradigm, and you want to talk about the exam now, right? Okay, so here's what's going to be on the exam. I'm not going to tell you, obviously, exactly which questions are going to be on the exam, but here's going to be the format of it. The format is going to be, the first question is going to take one page, and it's going to have multiple short answers. And the first question will be lots of scheme expressions, as if you typed it in, as if I typed it in, and then you tell me what comes out. Are you with me? So what you need to do is you need to be familiar with all the functions that we used up till now. And let me also tell you that I have just finished uploading all the slides and all the notes. So actually you have, if you want to know what we've done, is all you have to do is just go through the notes. So I typed up those lecture notes, and those have all the demos of all the stuff that we've done. So what I recommend you do to know what it is that you have to know, you should be able to predict all the ones that we did. You see what I mean?
They're all in the
So
notes.
like
They're all in the notes.
the ones we defined as well, not just the built-in scheme.
Well, definitely the built-in scheme stuff, but actually on the no, hold on. On the first page, I will not ask you to know the stuff that we wrote.
Okay.
So the first page will be all the scheme built-ins. You know, you have to know the difference between append and list and that kind of stuff. Are you with me on that?
Yeah.
And that's going to be there'll be A, B, C, D, E, F, and I'll just give you an expression. So that's not a design, that's an analysis question, all right? So you need to be able to know all those scheme functions, okay? Now, and then the rest of the exam is going to be writing scheme code. And many of the questions will be from the exercises. okay, from the homeworks. But there will be probably a couple that are not from the exercises. In fact, there will definitely be one or two that are not from the exercises. So to use what knowledge of scheme that you have to apply to a situation that you haven't seen before. But these schemes, it's a really, I really like, one of the reasons I like this paradigm is because the functions that we write are all fairly short, but on the other hand, you have to, conceptually, you kind of have to know what's going on in order to be able to write them. So there will be a lot of scheme coding on the exam.
Should we know like quilt stuff?
Oh, you know, quilt, let's just say no. Actually, I'll tell you what. And even the fractals, well, the fractal, well, no. Let's say no quilt, no fractals. Is that good?
Is the fractals the one with triangles?
Yeah.
Yeah, oh my goodness.
There's enough. We have enough, there's enough to do. Oh, now,
Any of the tests, no quilt, no fractals.
no quilt, no fractals. Now, I will tell you, I think, I'm repeating this. I will tell you, there's guaranteed one question that will be on the exam. And you know which one that one is, right? You have to be able to state the halting problem and prove that it's undecidable. And with that, you need to know how to write those functions. You can prove it in scheme, the way we did it. Do you remember how that worked?
No, but I
You don't, no, but you will. What chapter was that in? You want to review that?
Yeah, please.
Yeah.
Okay, we can review that, since we know that one's going to be on there. Okay, so here's the halting problem, right? And the question is the following. Is it possible to write a program that does halt that can determine whether any other program would halt if it were executed? And so is it possible to write that in general? We know that there are specific ones that we can analyze and predict whether or not it will halt. But the question is, can we write a program that would do this in general? And obviously, the program can't just run it and see if it halts, because no matter how long it runs, you wouldn't know if it's going to halt in the next minute, you know. So it can't just run it. That's the whole point. The point is, can it analyze it to see if it will halt? Is it possible to do that? And what's the answer? No. Okay, so that's the statement of the halting problem. Is it possible to write a program that does halt that can determine whether any other program would halt if it were executed? And the answer is no.
Did you say we have to write this?
Yeah, you need to know how to state this. Yeah, that's important. It's important to not only be able to prove the halting problem, you need to be able to state it. Yeah. And so this is not very mathematical description of it, but it's good enough for our purposes. Are we good? And the answer is no. So now you need to be able to prove this. And so you need to be able to, and you also need to be able to sort of do this kind of quickly, because all right. So now, does everybody agree? Return 7, lambda 7. That's pretty easy to write, don't you think? Okay, so return 7. And then the other one, what's the other one you have to write? You remember? Yeah, and what did we? Loops forever. And how do you write loops forever?
Define.
Lambda, parentheses, and then what? Just loops forever. Okay? So define loop forever, lambda, loop forever. And we know that we know that return 7 is going to return 7, and loop forever is going to loop forever, right? And now what do we do? Okay, so there's two functions you have to write. Now what other functions do we have to write? Do you remember what they were? Well, yeah, well, okay, actually before we go any further, maybe we better state what proof technique are we going to use? Yes, we're going to use proof by contradiction. And how does proof by contradiction work? We assume
Assume that
you can do it and show
that it's impossible.
and show that leads to a
False.
contradiction. Okay, is everybody with me? So, actually that should be on this slide somewhere. So we will define, yeah, so we will assume that you can write it. So, and what's the name of this program that we are going to write? Halts? Are you with me? And it's lambda, and how many parameters does halts take? 1. And that thing that it takes is a program, right? Now, you obviously can't write halts because we're going to prove that it's impossible to write halts, so there's a bug in this halts program. Okay? But anyway, that's what it's supposed to do. And so, and what we want halts to do is, if we give halts return 7, that should return true, and if we give halts loop forever, that should return false. So we are going to assume that we can define halts this way, such that that's what it does. Now, I hope I said, oh yeah, here's the proof by contradiction. So here's the proof by contradiction. We will assume it is possible to write halts and show that assumption leads to a contradiction. So that's an important part of the proof, is the technique you're going to use, proof by contradiction. Now, do you remember what we construct? And how to, now you have to remember what we, because this is part of the proof. We have to construct something, and what did we construct? Do you remember what we constructed? Debunk halts. And how did we construct debunk halts? What did debunk halts take as a parameter? Or did it? Maybe it didn't. Maybe it didn't take a... I think it might not have taken anything.
You said
We just wrote it with no... Yeah, and we said what?
if halts,
If halts...
debunk halts.
Yeah, we called it on itself. Okay, so we construct function, debunk halts, and here it is. So this you have to be able to write. So define debug halts, lambda, so no parameters, and it's just one if statement. If halts, debunk halts, call loop forever, otherwise call return 7. Or I should say return loop forever, or otherwise return 7. Are we good? And by the way, I showed this. You can put this code in Dr. Racket and click run, and this will compile. All this code compiles. It really does compile. We demoed that, right? Remember that? And now what's the reasoning that we do? Now what reasoning do we go through?
If halt says it will halt, it won't. And if it says it won't halt, it will.
Yeah, and how do you show that? What's the reasoning that we go through for that? There's two possibilities, either what or what?
Either debunk halts,
Halts,
or it doesn't.
or it doesn't. Okay, so A, debunk halts, halts. Well, if debunk halts, halts, then what will happen in the if statement? Halts, debunk halts will return what?
True.
Will return true. But if it returns true, what will execute? Loop forever. But if loop forever executes, so halts, debunk halts returns true, loop forever executes, but what's the problem? If loop forever executes, debunk halts does not halt. But we said we started with debunk halts, halts. So that's a contradiction. Are you with me? Oh, well, maybe debunk halts doesn't halt. So that's the contradiction, right? Oh, wait, maybe it's debunk halts does not halt. But wait a minute, if debunk halts does not halt, then what? Halts, debunk halts does what?
Returns false.
Returns false. But then what happens?
Returns 7. And then it halts.
Yeah, halts, debunk halts returns false, but then return 7 executes, which means that what? Debunk halts does halt. But now that's a contradiction. So no matter what the two possibilities are, can't be done. I mean, we have a contradiction. So therefore, the conclusion, the assumption implies a contradiction in all possible scenarios. Therefore, the assumption is false, and it is impossible to write halts. Isn't that amazing?
If the assumption implied a contradiction in only some of the scenarios, what would that tell us? Wouldn't it still be that mean that it's false? Like if A was worked, but B was a contradiction?
Well, that would not prove, well, then it would be possible. And you could predict what it would do. If you ran it, you could predict what it would do. Yeah, the question was, what if one of the cases it doesn't lead to a contradiction? If only one of the cases it leads to a contradiction, but the other one it doesn't, then what would happen is, the other one is what would happen.
What?
Well, look, we said there's two scenarios, right? If one of them led to a contradiction, but the other one didn't, the other one is what would happen. Wouldn't it be?
So they would do the same, they return the same thing. 'Cause
The other one would not be, the first one could not happen because it leads to a contradiction, so the other one would happen. And it would not be impossible because you could predict what it would do. But this is so counterfactual that we lose the, you see what I mean? That doesn't prove anything. That would not prove anything. That would just prove what would happen if you ran it. Are you with me? Of course, the way you could prove that it is possible would be to do what? To actually write halts. Then it's an existence proof. Are you with me? Then you can say, but I can't write it because here it is. But I know that you'd never be able to do that no matter how hard, because I would just write debunk halts and I'd say, okay, now tell me what's going to happen. And it can't. Oh, get your mind around that. That's pretty.
Wait, what if you just switch those two statements? The return 7 and loop for.
Oh, well, then what would happen? It would be consistent, wouldn't it? If debunk halts doesn't halt, it wouldn't halt, and if debunk halts did halt, if debunk halts didn't halt, so the question was, what happened if you just switched the loop forever and the return 7?
But since this counterexample exists, then doesn't that one counterexample prove that it never works? Or like it can't work?
No, well, debunks halts then would not really be debunking halts. Do you see what I'm saying? But halts would still, just because you write something that doesn't debunk halts, doesn't mean that it can't be debunked. It's just that you weren't clever enough in debunking it.
Okay, so this.
Do you see what I'm saying? This example shows you that it's possible to debunk halts.
Okay, got it.
Actually, what you asked is a very deep question. That was a good question. Yeah. It's falsifiable. Actually, we're going to be thinking about this in our next paradigm. You know what our next paradigm is going to be? It's going to be the logic paradigm. Okay. Yeah, it is going to be related to formal methods. Satisfiability and all that kind of stuff. Anyway. Well, this was a good review, I think, for this, because you know that this question is going to be on the exam. Any other questions? I think all the other stuff you can review, you have the materials to review, pretty much, now that the notes are all, and all the notes and all the slides are online now. You could even just tab through the slides, and I think that would be a way to go through the material. Are we good? And like I said, I've started grading the exam, the homework assignment, and I'll have that for you by tonight, electronically. All right, good deal. See you next time.